We're going to begin our conversation about stereochemistry with a new vocabulary word, which is isomers. If you break it down into the Greek, iso meaning same, and mers meaning parts. So the word isomers means same parts. So there's different types of isomers, and we're going to work our way towards the concept of stereochemistry. So the first type of isomer we're going to discuss is something called a constitutional isomer. And a constitutional isomer is when you have the same atoms, the same chemical formula, but different connectivity. So the chemical formula would be the same, just the atoms are connected in a different way. So let me give you an example of some constitutional isomers. One example could be this compound here versus this compound here. If you calculate the chemical formula for each of these compounds, you add up all the carbons, you add up all the hydrogens, you'll get the exact same chemical formula, but clearly these are two different compounds. The double bond is in a different place. So that is called a constitutional isomer. Same atoms, different connectivity. A second category of isomer is called a conformational isomer. And a conformational isomer is when you have the same molecule but different rotations around the bonds. We already talked about conformations. So same molecule, different rotation. All right, let's take a look at an example of that. So let's draw this molecule here. I'm adding some wedges and dashes to show some of these OH groups are coming out of the page towards us, and some of the OH groups are going into the page away from us. And I'll put another bromine here. And so let's draw a Newman projection of this molecule here. So let me put my little eyeball, my creepy disembodied eyeball, and we're going to look down the 2-3 bond. So if this is, we'll just number these, not carbons, but number the atoms. So the bromine will be 1, this carbon will be 2, this carbon will be 3, and this bromine will be 4. Let's look down the 2-3 bond. So we'll draw a Newman projection. And so there's the carbon 2 right in front, and then carbon 3 will be in the back. Okay, and we'll go ahead and draw this in the staggered form. And you can see that this molecule is staggered because you can see the sort of zigzag, and the zigzag is representing the staggering. So take a look. If our eyeball was here, what would be right above us would be the bromine. So I'm going to go ahead and put the bromine on the top position. And then go ahead and look at the carbon 3. Look at the bromine on carbon 3. It's going straight down. So we'll put bromine going straight down on carbon 3. All right, now let's fill in the rest of the groups. So also attached to carbon 2, there's an OH group, and there's also an H attached, an implicit hydrogen that's not shown. So imagine our eyeball is here, and we're looking at the molecule this way. The OH group will be coming out to our right. And the hydrogen, the implicit hydrogen, will be going in the last remaining position, which is out to our left. Okay. Now let's look at carbon 3. From the perspective of our eyeball, the OH group is going into the page, so that's going to be on the other side. It's going to be on our left. And there's an implicit hydrogen on carbon 3 as well, and that one's going to the right in the last remaining place. So this would be the Newman projection for that molecule. Now let's just do a conformational rotation. So let's go from being in the eclipsed form to the staggered form. So what I'll do is I'll leave the back carbon the same, and I'll move the front carbon. So the back carbon, we'll leave that totally still. And then the front carbon, I'll go ahead and kind of rotate that so that now the BRs are kind of on top of each other. The H's are on top of each other and the OH's are on top of each other. So can you see how I rotated that? I just sort of took this bromine and rotated it all the way down so that it's on top of the other bromine. And so if I take this bromine and rotate it to be on top of that bromine, then this OH group will rotate to be on top of that OH group, and this H will rotate to be on top of that H group. So 180-degree rotation. All right, now we can translate that rotation back into the bond line drawing. And so now the bromines are going to be eclipsing with each other. So I'll draw it like this, where the kind of, instead of the bond zigzagging, the bond looks kind of like a U shape, an upside down U shape. And now the two alcohol groups are eclipsing each other, and they're both kind of on the left side. So we'll make them both dashed like that. And so this would be the exact same molecule. So this guy and this guy are actually the exact same molecule. They're just rotated a little bit differently. So this we call staggered, and this we call eclipsed. But they're really just the same molecule, just rotated. Just like you're the same person, if you turn around, you're still you. So these are not really different molecules at all. These have a special word called conformational isomers. So this compound and this compound are conformational isomers. Sweet. Okay. Now that I've mentioned these two types of isomers, I want to mention a new type of isomer, and that is the stereoisomer. A stereoisomer is when you have the same atoms with the same connectivity. So the same atoms, and they're connected in exactly the same way. Okay. The only difference is a slightly different 3D shape. So like the shape that the molecule takes up is a little bit different between stereoisomers. So we'll say different 3D shape or bond direction is maybe a better way to say it. Okay. One important factor about stereoisomers is that they cannot interconvert by a conformational change. So meaning you cannot rotate the bonds to make the two molecules equivalent. The difference in bond direction is permanent in a sense. So let me show you an example of what I mean by that, of stereoisomer. So let's take a look at an example. Here's a lovely alkene. It's got two chlorines on it. Okay, so there's one molecule, it's an alkene, versus, how about this? Okay, so comparing these two molecules, they both have the exact same chemical formula. They both have two hydrogens, they both have two carbons, they both have two chlorines. They both are connected in the exact same way, meaning this carbon here has a hydrogen, a carbon, and a chlorine on it, and this carbon has a hydrogen, a carbon, and a chlorine on it. Same thing with this molecule. This carbon has a hydrogen, carbon, and chlorine. This carbon has hydrogen, carbon, chlorine. So it's the same atoms, the same connections to those atoms, but there's a difference. These molecules are clearly not the same. There's a directionality that's different. In this molecule, the chlorines are on opposite sides of the molecule, pointing away from each other. But in this molecule, the chlorines are on the same side of the molecule, pointing in the same direction. Now we can't rotate the double bond. Remember, you cannot rotate a double bond because you would break the pi system. You have those overlapping p orbitals. You cannot rotate a double bond. So there's no conformational change that would allow us to interconvert between these two structures. So these two structures are said to be stereoisomers. Let's take a closer look at this on the next page. And so we're going to start talking about the stereochemistry of alkenes. Okay, so there is a very casual way to distinguish the stereochemistry of alkenes. And they are as follows. Let's imagine we have this alkene versus this alkene. Again, these are stereoisomers. It's the same chemical formula, just different directionality of the bonds. In this case, the first alkene is said to be trans. It's said to be trans because the groups on the alkene are facing in opposite directions. And the other alkene is called cis. That is because the groups on the alkene are facing in the same direction. Now, which one of these do you think is more stable? Which one of these is going to be lower in energy? Remember, when I say more stable, that means lower energy. Everything wants to be more stable. Everything wants to be lower energy. These two alkenes are not the same in terms of energy. It turns out that cis alkenes are typically more unstable. They're higher energy. And the reason is due to something called steric repulsion. And let me just kind of show a picture of what steric repulsion is. Let me draw that cis alkene again over here. And let me actually draw on the cis alkene the hydrogens on those two methyl groups that are coming off of the alkene. And on those two methyl groups, each one has 3 hydrogens, 3 implicit hydrogens that are not shown. And look what happens in the cis alkene. The hydrogens kind of get forced to bump into each other, which is high energy because those hydrogens have electrons making up their bonds, and so those electrons get forced to be really close to each other, and electrons want to repel each other. So this is a very unstable clashing of the forces. So they don't want to be like this close. It's way too close. It's way too uncomfortable for those hydrogens. So for that reason, cis alkenes are typically higher in energy, and I think this makes sense. When you have the trans alkene, those hydrogens have a lot of distance between them, so they're not bumping into each other. Okay, so this is pretty easy. This is not a hard concept to understand. Now we're just going to recognize that we can have trans alkenes and we can have cis alkenes, no problem at all. However, it gets a little bit tricky. Let me ask you a question. Is this cis or trans? I'm going to draw an alkene here. Put an alcohol group on it. I'll put a chlorine group on it. I'll put a methyl group down here, and I'll put an H over here. So this is hard to assign cis or trans because what do we consider the biggest groups here? We've got stuff on every atom. So for example, maybe you think this is cis because the chlorine and the OH are on the same side. Or maybe you think it's trans because the OH and the methyl group are on opposite sides. It's not clear whether this is cis or trans because there's too many different groups there. So we use a more exact way of talking about cis versus trans. We use a different form of nomenclature called EZ nomenclature. So we'll just say this is neither. It's too confusing to say cis or trans. So we're going to use EZ nomenclature instead. And that will make our job much easier. Let me show you how to use EZ nomenclature, and I think this is a lot of fun because it's kind of like ranking. It's kind of like one of those shows where, people get eliminated, and they get to go home. I'm so sorry, you're chopped, that kind of thing. Okay, so let's take a look and let's see who's going to get chopped in this competition. So I'm going to go ahead and draw my alkene again down here. H here. We've got a chlorine, OH on this side, and we've got a chlorine on this side. And what you want to do is split your alkene into two teams, team 1 and team 2. And so what I'm going to do is I'm going to just draw a dotted line right down the middle. And then we're going to have a competition on each side of that dotted line. Okay? And we're going to use something called the Kohn-Ingold Prelog rules to choose a winner. So we're going to use Kohn-Ingold Prelog priority rules. Now that is a mouthful, so sometimes you'll see teachers, including me, just call these the SIP rules, Kohn-Ingold Prelog rules. And there's actually 3 parts to these rules, but we only need to use part 1 for this one. So part 1 says, assign priority based on atomic number. Easy. Assign priority based on atomic number. So we'll look at each side and we'll choose a winner. So first we'll choose from team 1, which is on the left. Who has a higher atomic number, chlorine or carbon? Well, you can look at the periodic table to remind yourself that chlorine has a higher atomic number than carbon. So all right, I'll close that. Carbon has a lower atomic number than chlorine. So that means chlorine is our winner. So I'll go ahead and put a red box around chlorine is our winner on team 1. Now we'll do the same thing on the right side. Who has the winning group on team 2? Who has a higher atomic number? Look at the atom that's directly attached. Is it oxygen or hydrogen? Who wins? Hydrogen has a lower atomic number than oxygen. So oxygen is our winner. So we'll just put a box around oxygen. And so you can see here that our 2 winners are on the same side. Our 2 winners are on the same side. They're both on the top. If one was on the top and one was on the bottom, that would be different sides. But our chlorine and our OH are both on the same side, so we call this Z. Z. Which is standing for the German word zusammen. I'm probably butchering that. I hope someone here speaks German. But zusammen is the German word for together. So here's how it works. If the highest priority groups are on the same side, this is called Z for zusammen. And you know how I remember this? It's kind of stupid. The bigger groups are on the same side. That's kind of my German accent. So the bigger groups are on the same side. That would be Z. If the higher priority groups are on the opposite sides, we call that E. And that is for the German word entgegen. Again, I'm sorry if I'm butchering the German here, but entgegen, which means different or opposite. So remember, Z means on the same side, and E, entgegen, means on opposite sides. All right, so that's a fun example. Shall we do a harder one? Can we make this a little bit trickier? Absolutely we can. Let's take a look at what happens when there is a tie. That's always the fun thing in chemistry. What if we have a tie? What do we do? Well, the Kohn-Ingold Prelog people, they thought of everything. They thought of what to do in the case of a tie. So let's take a look. I'm going to draw a really complicated alkene here. And we're going to put an ethyl group on this position. We'll put a aldehyde on this position. And we'll put a ether down here. And how about a tert-butyl group down there? Okay, that's pretty good. Okay, now let's continue with the remaining two parts of the CIP rules. I said there were 3 parts. Part 2, remember part 1 was just the highest priority group is based on atomic number. Part 2 says if first atoms tie, which is what is going to happen in this example, meaning you have like carbon and carbon. How can you decide between carbon and carbon? If in this situation, make lists of atoms attached to them. The list with the higher atomic number for the biggest atom wins. Sounds confusing, but it's actually pretty easy and pretty fun. And one more rule to keep in mind, double bonds are treated as 2 bonds to the same atom. All right, so let's apply these rules to this example. And so what I'm actually going to do is I'm actually going to color code the different attachments to our alkene, and we're going to make those lists. So looking at our alkene here, why don't we call this attachment yellow? This attachment will be green. I'm highlighting the atom that's directly attached to the double bond. We'll call this one orange, and this guy's pink. Okay, so yellow, green, pink, and orange. So let's start here with yellow, and we'll have green, we'll have pink, and we will have orange. Okay, we're going to make a list of all the atoms connected to those, because if you look at all of these atoms, what are yellow, green, orange, and pink? They're all carbons, so they're all tied. They're all tied. Remember, of course, we are only going to be looking at for the winner in Team 1 and Team 2, so let's go ahead and draw that dotted line right down the middle of the alkene to split up the 2 teams. Okay, so now let's do Team 1 first. What atoms are attached to yellow? What atoms are attached to yellow other than the alkene itself? So if you look at yellow, it's attached to a carbon, and it's also having 2 implicit hydrogens on there. So we're going to make our list as carbon, hydrogen, hydrogen. Now let's do our list for green. Green is attached to 3 carbons, so it's going to be carbon, carbon, carbon. All right, so now we just go down our list and we choose the first winner. So round 1, it's a tie, carbon and carbon. But round 2, it's between hydrogen and carbon, carbon wins. So that means green wins overall. So I'm going to put a check mark in green, green wins. And so I can also put a box around the green carbon on Team 1. Now let's do it for pink and orange. What's attached to pink? We have oxygen, but it's a double bond, so that counts as 2 bonds to oxygen. So oxygen, oxygen, carbon. And notice that I list them out in order from highest atomic number to lowest atomic number. So this will be oxygen, oxygen, carbon. Those are the atoms that are attached to pink. Who's attached to orange? We have oxygen, and then there's 2 implicit hydrogens on that carbon. So it'll be oxygen, hydrogen, hydrogen. All right, so let's see who wins, pink or orange. Well, round 1, they tie. They both have oxygen. We go to round 2. Pink has oxygen, but orange only has hydrogen. So Team Pink is the winner. Boom. So now we'll go ahead and put a box around Team Pink. And what we can see is that the two winning groups are on opposite sides. So this is going to be E. So our alkene is E. Not too bad, right? Not too bad. Okay, so there'll be more practice problems like that on your problem set. There'll also be practice problems like that on the quiz. So make sure you understand what's going on there. It's kind of fun. I enjoy it. All right, let's change gears a little bit. We're actually almost done with this lesson. I want to introduce another type of stereoisomer. And this is kind of stereoisomer does not involve double bonds. This is the kind of stereoisomer that you'll sometimes see with alkanes. And so before we talk about that, I want to introduce two more vocabulary words. And those words are chirality and enantiomers. Okay, so let's first talk about what is a chiral molecule. A chiral molecule is not superimposable on its mirror image. That's the definition of chiral. It means it's not superimposable on its mirror image. That is the definition of chiral. The word chiral comes from the Greek kyros, meaning hand. So chiral means like a hand. And because our hands are in fact chiral, our hands are chiral. Let me explain that to you. And you can see it right in front of you. So hold out your hands right now. Look at your hands. And you can see that your hands are actually mirror images of each other, aren't they? Like if you held your left hand next to your right hand, it's like there's a mirror between them. They're reflected to make each other. But they're not the same. Take your left hand and try and line it up perfectly with your right hand. You'll find that you can't do that. This doesn't count, right? This doesn't count as lining up perfectly because this hand, the palm is out facing the outside. And for this hand, the palm is also facing the outside. What I mean by lining them up perfectly is trying to completely and perfectly overlap them the same way, but you can't because your thumbs are sticking out in different directions. So that's why, we have left-handed gloves and right-handed gloves. If it wasn't for the fact that our hands were not superimposable, then one glove would fit all hands. But we know that that's not true. So actually, there are some gloves that are designed so that they fit either hand, but a truly, good glove is there's going to be a left-handed version and a right-handed version. And so molecules also have this property where they can be existing as mirror images but not be superimposable with each other. Let me show you an example of a chiral molecule. So I'm going to go ahead and draw a chiral molecule here. Chlorine up here, OH here, H here, and a methyl group down there. And we'll call this molecule A. And now I'm going to draw a little dotted line here to represent a mirror. And let's see what this molecule would look like in the mirror. I'm just going to kind of try and draw its mirror image. Okay, and we'll call this molecule B. So it's kind of hard to see this, and what we'll do in class, maybe we'll try and build a model to see this a little bit better. But imagine we wanted to try and line these molecules up on top of each other. You couldn't do it. If you took this molecule and tried to rotate it so that it was facing the way that molecule A is facing, then this OH group would not be facing this direction, but rather the OH group would be in the back. And try as you might, you would never be able to perfectly overlap these two molecules. These two molecules are not the same. They are stereoisomers. They are chiral. So here are some facts about these two molecules. Fact number 1. A and B are stereoisomers. They are stereoisomers because they're the same atoms, they're connected in the same way, but they differ in their shape or direction. So that meets the definition of stereoisomers. Point 2. A and B are non-superimposable mirror images of each other. And because 2 is true, that A and B are non-superimposable mirror images of each other, therefore A and B are said to be enantiomers. A and B are enantiomers. The definition of enantiomer means that the two molecules are non-superimposable mirror images. It was too many words to say blah, blah, blah are non-superimposable mirror images, so they just replaced that whole phrase with the word enantiomers. And that is a relationship between these two compounds. These two compounds are enantiomers of each other. So let's switch gears for a second and just try and identify, is a molecule chiral or not? How can we tell if a molecule is going to be chiral or not? It's a little bit tricky to be constantly drawing mirror images and seeing if it's going to overlap. There's a super easy shortcut to tell if a molecule is chiral. So a chiral molecule has no plane of symmetry. That is always true. If there was a plane of symmetry, then there would be a way to superimpose on its mirror image. So let's take a look at an example. How about the molecule we just had? Okay, here's the molecule that we just had. It is chiral because there is no plane of symmetry. There is no plane that I could draw that it can internally be symmetric. Okay, there's no plane I can draw to where this molecule can be internally symmetric. So we call this molecule chiral because it has no plane of symmetry. And sometimes the carbon that's in the middle, or the atom that's in the middle, that's sort of all of this non-symmetry is occurring around, is called the stereocenter. Or sometimes called the stereogenic center. It is the point inside the molecule that's central where all of this asymmetry is occurring around. That is called the stereocenter. Versus, let's take a look at another molecule here. Instead of having an OH there, let's just put an H there. Same molecule, just replacing the OH with an H. And now look, there is a plane of symmetry. I could draw a plane kind of cutting this molecule right down the middle, right in between the hydrogens. Can you see that kind of? If I just slice this right down the middle, right between the two hydrogens, there'd be an internal mirror plane that is an internal form of symmetry. So because this molecule has a plane of symmetry, it's said to be achiral because it has a plane of symmetry. And so this carbon in the center here is not a stereocenter. The carbon in the middle is not a stereocenter. So even this is a little tricky. I mean, I don't know about you, but when I first learned organic chemistry, I was not very good at seeing planes of symmetry. Could I make this even easier for you? Of course I can. Here's a quick way to tell if a carbon is a stereocenter. And remember, if a carbon is a stereocenter, then you're going to be looking at a chiral molecule. There's one exception. We'll be talking about that a little bit later. But for now, that's true. So for a carbon, or any atom really, but in this class it's going to be carbon, to be a stereocenter, it must have 4 unique groups. Four unique groups attached. I ran out of room. Okay, so I'm going to draw some molecules and you're going to be able to tell me, does that carbon have 4 different groups attached? All right, let's take a look at this. All right, now one place you really want to look for a stereocenter is whenever you see wedges or dashes coming off of a molecule. That typically is a sign that you want to look at the carbon that the wedges and dashes are coming out of and check to see if it has 4 unique groups. Just because you see wedges and dashes does not mean it is a stereocenter, but it may be a stereocenter. All right, look at this carbon here. Does it have 4 unique groups attached to it? It certainly has 2 unique groups here. It has a chlorine and a hydrogen, and then it also has 2 additional unique groups. It has a methyl group and an ethyl group. So remember, don't just look and see like, oh, carbon and carbon, they're the same. No, you need to consider that this is an ethyl group and this is a methyl group. So yes, this carbon does have 4 unique attachments. This molecule has a stereocenter and it is chiral. Let's take a look at another example. Okay, again, we're just looking to see if there's 4 different groups attached. Look at the carbon, the potential stereocenter. There's a chlorine, a hydrogen, but then there's 2 methyl groups. So that is not 4 unique attachments, so it's achiral. You need 4 unique attachments, and this one only had 3 unique attachments. Let's take a look at another example. All right, let's take a look at our possible stereocenter. That's this carbon right here. It's got a bromine. It's got a hydrogen not shown, but there's an implicit hydrogen there. There's an implicit hydrogen. And then there's a carbon to the left and a carbon to the right. But the carbon to the right is part of a double bond. That is different than the carbon to the left. So this is 4 unique groups. This molecule is chiral. Next up. Okay, same molecule as the one before, it's just no double bond now. No double bond. So we have a bromine, that's group 1. We have a hydrogen, not shown, it's implicit. And then we have carbon to the left and carbon to the right. But the carbon to the left and right, they connect back together, and there's no difference between them. So the left side is the same as the right side. So that is not 4 unique attachments. That is going to be achiral. Let's take a look at another example here. All right, let's take that cyclohexane again, put a bromine, and then let's put a methyl group down here. All right, let's take a look at this molecule. So this bromine here, does it have 4 unique attachments? It does. It's got, this carbon has bromine attached. It has a hydrogen attached, not shown, but it's implicit. We have some carbons over on the right, and then we have some carbons over on the left. But the carbons on the left have a methyl group coming out of it. The carbons on the right do not. So this is going to be chiral. By the way, how many stereocenters does this molecule have? How many stereocenters does this molecule have? Well, we know already that this is a stereocenter because it has 4 unique attachments. What about this carbon? Does this carbon have 4 unique attachments? It sure does. This carbon has a methyl group. It has a hydrogen, not shown, implicit hydrogen. It has carbons up here, but these carbons are close to a bromine. And it has carbons over here, but these carbons are not close to bromine. So you have 4 unique attachments. So this molecule actually has 2 stereocenters, one stereocenter here and another stereocenter here. Notice this is a stereocenter even though there's no wedge or dash here. Even though there's no wedge or dash here. It's not required to have a wedge or dash. All you need for a stereocenter is 4 unique attachments. The wedges and the dashes kind of help you focus on what part of the molecule you might want to consider. And then let's do one more example here. This molecule here, the aldehyde. We take a look at this carbon here. Does it have 4 unique attachments? Well, it has oxygen, hydrogen, and carbon. There's no 4 unique attachments. There's only 3 unique attachments. So this is going to be achiral. No stereocenter. All right. All right, so why don't we stop right there, and we'll continue on our conversation about stereochemistry tomorrow.